So what is the physical state of thought? What is the cause of your emotions, of decision-making, our passions, our pains, and everything else? Well, it's the brain. Well, it's the brain, and it's said to be the most complex machine in the known universe. You might expect, given all it is and given all it does, that will look very pretty. Philips shimmering lights and glass tubes and mysterious colors. But in fact, it looks very kind of gross. It's like a very day-old meatloaf. It's grey when you take it out of the head, and inside the head is bright red because of the blood. In fact, it turns out very surprising that the cause of our mental life, of our consciousness, is meat. In fact, you could eat if people have alien brains, if had brain with cream sauce, not human brain meat you, but I've had brain with cream sauce. It's not bad, but it makes the puzzle all the more harder. How can this special thing give rise to mental life? That's the question I want to explore in this lecture and the rest of the lectures. I want to do so by starting with the smallest related parts, different parts of neurons. Then explore how the nerves are connected together, how they are wired up, how we form different subparts of the brain, like the hypothalamus and the frontal lobe. Finally, talking about the brain in the larger perspective, look at the two halves of the brain, the left half and the right half, and how they interact. Now there's a lot of stuff in the brain, a lot of chemical stuff, a lot of different parts, but where the action is, the part that does the thinking, the part that is the focus of most of our research, in the neurons. It's not an accident they call the study of the biology basis of our neuroscience, because it all comes from the neurons. So you can see here a picture of neurons interaction together. Here's a diagram that depicts a typical neuron. So what you see is the dendrons, and dendrons receive signals from other neurons. Either interaction excitatory like pluses or inhibitory minuses. Then they get to the cell body, which sums out those pluses and minuses. When you reach a certain threshold, a certain amount of pluses, the neuron freeing. Freeing takes place without the axons, and the axon is much longer than the dendrites. In fact, for some motor neurons, it's very long indeed. There's axon running from your spinal cord all the way to a big toe. You could think of it all the relative size of things in terms of basketball and a 40-mile garden house. Surrounding the axon is what's called a melange. The melange you can think of as insulation is fatty tissue like insulation on wire. So the information is you can think of its insulation as fatty tissue like insulations on wire. So the information comes through the dendrites and summed up in the cell body, and it's transmitted through the axons. So what neurons do is they sum up and transmit information, and we know there are a lot of them. By some estimates it's 100 billion, or the estimates tend to be very different and very out, but there are billions upon billions of neurons, and each connect to thousands, maybe tens of thousands of our neurons. So the fact that you have something of this danger of complexity, this danger of structure which there is no way to replicate in any machine, the numbers are just too big, is how people might describe the brain as the most completed machine in the universe. At least this fitting is made of meat maybe, which is kind of disappointing, but at least it shows its incredible internal structure. So neurons come in three flavors. They are sensory neurons, which take in information for environment for external world. There is motor neurons, which go from the brain out to your motor control. So, if you touch something hot and you feel the pain, and that in sensory neurons. If you rent your hand back or you reach for something, that's motor neurons. Finally, there's interneurons, which connect different neurons without making contact with an external world. Yet thought sensations or thought motor actions, action. Now, the main thing to think about the neurons and neurons fearing is that it's all or nothing. It's like throwing a gun or sneezing. Neurons are far, and they don't. Now, you might think it's a little bit strange, practically, when you think about sensory neurons, because your experience seems to be a continuum. So you have sensory neurons in your eyes, and you can distinguish from a very dim light and a very bright light. You have sensory neurons in your fingers, and you could just distinguish between gently touch something versus being stepped on the tip of your finger of something. But still, the neurons are all or nothing. The way we get to this quantity of experience is that neurons can code for intensity in different ways. So one way is in terms of the number of neurons that fire. If X neurons corresponds to mild experience, X times 10 neurons may correspond to an intense experience. Another factor is the impulse frequency of individual neurons, and individual neurons might denote a mid-sensor by down fur, while it might denote an intense situation with fur. So you have neurons, and the neurons talk to each other. They talk to each other because axons. On axons of one neuron will communicate with the dendrites of another neuron. A long time ago, people used to think that neurons were wired all together like a computer, but in fact, neurons don't actually touch one another. There is a gap between the axon terminal of one neuron and the dendrite of another one. A very tiny gap. Typical of like one exactly of my right. This gap is known as a synapse. When one neuron fires, the axon releases neurotransmitters. These are chemicals that shoot out over that gap and affect dendrites and another neurons. As I said before, the effect of those neurons transmitters could be excitatory, which is that they raise the energy, so they increase the likelihood of neuron freeing or inhibitory, so that they bring down the likelihood of a neuron firing. What's interesting is that different neurons shoot out different neurotransmitters, so they have different effect on other neurons that they made contact with. In fact, a lot of psychopharmacology both attempts to cure various psychological or physical disease by giving machines or recreation psychopharmacology designed to increase pleasure of different forms, or sometimes help people work or help people focus. Works by feeding with the neurons meters, and this can be either an antagonist that lower down intensity or things by bidding to the dendrites, making it hard to create more neurotransmitters, or they can increase the amount of neurotransmitters available in different ways agonists. So you're ever pumping up the volume or turning down the volume. So we think about different drugs and their effects. There's Curare. Curare is a drug that is used by South American Indians. It's an agonist. It blocks motor nerves from affecting the musical fibers. It keeps your motor neurons from working, and what it does is it paralyzes you, and in larger doses, it kills you because motor neurons also keep your head beating. So, shut that down and you dare. The alcohol. No, alcohol also has an inhibitory effect. You might think that's strange because I drink alcohol. I get all excited and happy and goofy. But you have to keep this in mind here. The alcohol works is it inhibits part of your brain that does the inhibits. So you have part of your brain that says, don't say that the other person. Keep your pants on. Stop yelling. And alcohol basically inhibits that part of the brain, making you more exuberant. Then other course of things. In the course of drinking too much, it also inhibits other parts of the brain. So you could pass out the fall on the floor and letting out doses there. So, both Curare and alcohol in different ways bring things down. Other drugs bring things up. So, amphetamines, for instance, increase the amount of norepinephrine, which is another neurotransmitter that's responsible for genetic general arousal, and this is how drugs like speed of cocaine work. Other drugs like Prozac or L-DOPA influence neurotransmitters in ways that they increase, for instance, the supply of dopamine or serotonin, which can be relevant for uses like Parkinson's, which seems to be related to like dopamine, and depression, which is related to little serotonin. So those drugs work by influencing neurotransmitters, whether by directly pumping in more neurotransmitters or increasing the supply in different ways, or stopping them from having effect by binding them or sucking them up in different ways. But the work found the effect of neurotransmitters, so the more general idea is the way neurons lead to thinking is that they form clusters or networks. Those clusters and networks are computational devices do interesting things like recognizing faces, or walking upright, or understanding sentence, or doing math, or experiencing a great sadness, or falling in love, and so on. We now know that possible because you are great computation machines that were in created ways, that if you are a computer machine in great complicated ways, it can do mathematics, play chess, do fleet simulator, and so on. So you may be interested in the project of computational neuroscience, which tries to ask the question: how are neurons wired up to do interesting things, and uses our own sources at completion there as a model. Then something takes the inference the other way around, which is you can see how people do it, and then use this knowledge of how people do it to create computational systems, computational systems that can do it well. So, how is the brain wired up? Well, you might imagine that it's wired up like a portable computer, like a laptop, like the sort of computer you're looking at now. Into some regards it is, but there are couple of reasons who it can be, and both of them have to do with how well the brain works. So first, the brain is highly resistant to damage. If you get enough to the brain, if you get damage to the brain, it won't typically shut down the whole system. The information and captured somehow distributed across neurons in such a way that makes them extremely resistant to damage. While in contrast, somebody could open the back of your laptop, pull out chip, and the whole thing's interrupted. The whole thing will stop working. But the brain is wired up in a created way that makes it highly resilient. The second thing is the brain is wired up in such a way that makes it work very fast. Some computers can do millions of operations per second because they are purely electrical. But brain is much slower and can spend the time to do many steps. So to put it a different way, if your brain was wired up like a computer, it would be so slow as to be entirely usable. It has to be wired up in a way that's more effective, that allows for the slowness of brain tissues and neurotransmitters, and can still compute things at a human level, which is often blindingly fast. Because of this, there has been a high interest in massively parallel systems and complicated neural networks, which are wired up as they believe the brain does, and as such, we are helping computers to do things based on our understanding of the brain that they could never do before. The details of this is something we're going to talk about throughout the course. We're not actually going to end up explaining different passes directly in the terms of neurons, because we can't, and because we want to have high-level explanation. So, when talking about how people learn language, or how do they recognize faces, we're not going to talk much about neurons in particular, but we will talk about different brain areas and how they work. The assumption is that everything we talk about in more functional ways can ultimately reduce down to large networks of neuron systems, and that in turn will ultimately reduce down to the specific behaviors of the specific neurons that we're looking at.